In this video, we're going to find the general solution to a linear system in the case of complex eigenvalues. So suppose we have a system of differential equations given in matrix form like this. So the first step in solving a problem like this is to find the eigenvalues and their associated eigenvectors of this matrix. So you pick your favorite way to find eigenvalues and eigenvectors, and you'll come up with these eigenvalues. Of course, since they're complex, they always come in conjugate pairs. And some examples of an eigenvector you might come up with: I over 2, 1, and minus I over 2, 1. So the good thing about when you get complex eigenvalues is that you actually only need one eigenvalue-eigenvector pair. So we actually don't care about this second eigenvalue-eigenvector pair at all. So how do we proceed? It's the same as in the case of real eigenvalues, in the sense that we now know how to create at least one solution. So I'll write yc of t, the c standing for complex. And we get e to the eigenvalue times t times the eigenvector, the associated eigenvector. So this is a perfectly good complex solution to our differential equation, to our system of differential equations. The problem is it is complex, and we want a real general solution. So what do we do next? We separate this into real and imaginary parts. So to do that, we're going to use the fact that e to the it, well, we're going to use Euler's formula. So we're going to expand out that e to the I2t. And then we're going to multiply this out. So what we get is e to the t, I over 2 cos 2t, minus 1/2 sine 2t, cos 2t plus I sine 2t. And then we're able to separate out the real and imaginary parts. So we have e to the t minus 1/2 sine 2t cos 2t. And then we take all the parts with I in them, and we pull the I out. I e to the t 1/2 cos 2t sine 2t. So here we have our single complex solution, and we've separated out into a real solution plus I times an imaginary solution. So we've separated out our complex solution into real and imaginary parts. So we can write the complex solution as y real of t plus I times y imaginary of t, where these turn out to be both real valued solutions to the original system. So because we have two real valued solutions to our original system, we can express the general solution as a linear combination of the real valued solution, of the real part, and the imaginary part. So that means our general solution is, in fact, And that's it. This is our general solution for unknown constants k1 and k2.